You know, I was thinking about how frustrating the first 6 months in this hobby can be.
Oh, yeah, it is. It's definitely a learning curve.
Right, because you spend all this time acting like a precision mechanic. You square the frame with machinist blocks, you dial in the belt tension, you buy like a ton of desiccant to dry your filament.
Exactly. You get the hardware absolutely flawless.
Yeah, the machine sitting there is mechanically perfect. But then you slice apart, you hit print, and it just looks terrible.
The corners look like marshmallows, yeah.
Right. Swollen corners, weird gaps in the perimeters, terrible layer adhesion. And it is just super frustrating when you know the physical machine is perfect, but the plastic just is not behaving.
I see it constantly, intermediate makers hit this massive wall. They stare at their perfectly trammed bed and like their bone-dry spool of PTG, and they just cannot figure out why the mechanical perfection isn't translating to the physical object.
Because they focus entirely on the hardware.
Exactly. They completely forget that the hardware is blind. It only does exactly what the software tells it to do.
Right.
If the translation from the 3D geometry to the motor movements is flawed, a $10,000 machine will still just produce garbage.
It really is the invisible brain of the whole operation. So today, our mission for this deep dive is to explore OrcaSlicer. We are going to tear it down to the studs.
That sounds like a plan.
We want to figure out if it is actually worth ditching something like Cura to relearn a completely new system. And to do this, we are pulling from two really great sources. First, a comprehensive setup guide from a Monday Hub article, and second, a Thursday support article that does a real-world workflow comparison between OrcaSlicer, Cura, and PrusaSlicer.
Those are solid sources. It really helps build that decision guide framework.
Yeah, because switching slicers isn't just clicking a different icon, right? It is like choosing a totally different physical workshop. You could have the best tools in the world, but if your workbench is messy and the lighting is bad, your projects are going to suffer.
That workshop analogy is honestly the perfect lens for this. Because before we even talk about, specific retraction settings or whatever, we have to look at who built the workshop.
Right. The lineage.
Yeah, the family tree of these programs.
Yeah.
Understanding where they come from explains how they behave. It's not magic, it's decades of open source legacy code.
So let's trace that lineage. A massive portion of the modern slicing ecosystem goes all the way back to Slic 3.
Slic 3, right, the early reprap days.
Exactly. And then Prusa Research took that open source code and turned it into PrusaSlicer, optimizing it for their bed slingers.
Right.
Then Bambu Lab came along, and they didn't write a slicer from scratch. They took the PrusaSlicer codebase and forked it to create Bambu Studio.
And that timeline brings us directly to OrcaSlicer. But here is where a lot of people get the facts totally wrong.
Oh, I see it on forums all the time.
Yeah. OrcaSlicer is a fork of Bambu Studio. And it launched back in July 2022. But when it launched, it was actually called Bambu Studio SoftFever.
Because SoftFever is the developer.
Yeah, exactly. It is developed by SoftFever, not Bambu Lab. It is a fully independent, community-driven fork.
And that is a huge misconception. People think, well, I don't own a Bambu printer, so I can't use OrcaSlicer. Or they think there is some, paid pro version they have to buy.
Right, which is completely false.
It's completely free. It is fully open source on Windows, macOS, and Linux. There is no paid version at all, and it has over 14,000 stars on GitHub right now.
That level of engagement is just staggering. Bugs get patched in days.
Yeah, the community velocity is insane. So going back to the workshop analogy, PrusaSlicer, Bambu Studio, and OrcaSlicer all share that same structural skeleton.
Right, they share the same base chassis.
Exactly. So if you know one, the dashboard of the others feels instantly familiar. But then on the completely opposite side of town, you have Cura.
Yeah, Cura is a totally different species. It is built by UltiMaker, and the underlying engine is called CuraEngine. It is absolutely not a fork of Slic 3 or PrusaSlicer.
It's a completely different manufacturer.
Exactly. It doesn't share a single line of foundational code with them. The math it uses is fundamentally different. So if you are moving from PrusaSlicer to Cura, it requires a complete mental reset.
Okay, so since the underlying engine dictates the user interface and the logic, how do these slicers actually connect to the hardware sitting on your desk?
That is the big question. It impacts everything.
Because, say I am an intermediate maker with a mixed fleet. I have an old Creality machine, a Voron I built, maybe a Prusa MK4. Which workshop do I choose?
Well, if you only run Prusa hardware, PrusaSlicer offers the absolute tightest integration. It's tuned by the engineers who made the printer.
That makes sense?
But if you want to install custom plugins, or if you need the biggest library of ready-made profiles for really obscure generic printers, Cura has historically been the answer for that.
But wait, if Cura has the biggest profile library and a massive marketplace for custom plugins, why wouldn't someone with a mixed fleet just default to Cura?
Because of the difference between native features and hacky workarounds.
Oh.
OrcaSlicer brings modern conveniences out of the box that Cura often requires manual tweaking or third-party scripts for. OrcaSlicer is the ultimate middle ground for a mixed fleet.
Because it's not just for Bambu hardware, right?
Exactly. It ships with out-of-the-box presets for Prusa, Voron, Creality, Anycubic, FLSun, and dozens of others.
That is super convenient.
It is. And it natively handles smart toolpath planning for multicolor setups. It handles network printing like LAN or cloud with live camera monitoring right inside the interface natively.
Right. You don't need a random Python script just to see your webcam.
Exactly. You just type in the IP address.
Okay, so I am sold on using OrcaSlicer for my mixed fleet. I download it, I pick my printers, and I am staring at the empty build plate. What is the very first thing I should actually do?
Well, do not just import an STL and hit slice.
Which is what everyone does.
Right, and it's a mistake. The first major benefit you encounter in OrcaSlicer is its built-in calibration superpower. It is the beating heart of the software.
Because it doesn't require you to go to third-party websites for test models, right?
Exactly. It generates them internally. You just click the calibration menu, and it algorithmically generates the exact G-code test for your specific nozzle.
So let's talk about the specific tests. Starting with flow rate. Why calibrate flow? If I have 1.75 millimeter filament and a 0.4 nozzle, shouldn't the math just be predictable?
In a sterile vacuum, sure. But we are melting complex polymers here.
Right. The plastic swells when it melts.
Exactly. Die swell. As it gets forced through the nozzle under immense pressure, the polymer chains compress. When they exit and hit the air, they relax and expand. And that expansion varies wildly between brands and materials.
So even if the extruder pushes exactly 10 millimeters of plastic, what actually comes out of the nozzle is a total guess unless you test it.
Right. If you just assume a 1.0 flow multiplier, you are guessing. So the flow rate test prints these small squares with flow ratios ranging from 0.92 to 1.28.
And you just look for the smoothest one.
Yeah. You inspect the top layer. Too low, and you get microscopic trenches between the lines. Too high, and the plastic pushes up into rough ridges. You find the perfectly flat square, and that becomes your permanent flow ratio for that spool.
Okay, flow rate makes sense. But the one that really intimidates people is pressure advance, or PA.
Oh, PA is a game changer, though.
Well, the software gives you two methods. You have the quick 10-minute line method or the really precise 1-hour vertical tower method.
Yeah, the tower is the way to go for real accuracy.
But let me ask you this. If I've been printing for a year and my PLA benchy looks fine just by slowing the printer down, is it genuinely worth spending an hour printing a pressure advanced tower?
Yes, absolutely yes.
Really? An hour?
Look, if you want to move from okay to perfect, you have to stop estimating. Slowing down is just a Band-Aid. We have to think about the fluid dynamics inside the Hodan.
Okay, break that down for me.
The extruder pushes solid filament into the melt zone, right? This creates hydraulic pressure. When the heavy print head approaches a sharp corner, it physically has to decelerate.
Right, the motors slow down so it doesn't just shake the printer apart.
Exactly. But the melted plastic inside is highly viscous. It acts like a loaded spring. So even as the motors slow down, that built-up pressure keeps forcing plastic out of the nozzle.
Ah, so that is why you get those swollen, bulging corners?
Yes. And then when the tool head accelerates away from the corner, the pressure is depleted, so you get under extrusion and weak bonding for the next inch or so.
So pressure advance is basically the software anticipating that physics.
Precisely. It is a setting that improves corner and detail quality. It retracts the filament slightly before the deceleration to relieve the pressure, and then advances it as it accelerates away.
And because every plastic is different, you can't just guess the number.
Right. You print the tower, and you inspect the corners to find the exact height where the corner is razor sharp with zero bulging. Doing this means you can print way faster without losing quality.
That is fascinating. Okay, what about the temperature tower? It tests 200 to 230 degrees for PLA and 230 to 260 for PDG.
Yeah, people usually just look at a temp tower to check for stringing.
Right. A block with the least strings wins.
But that is only half the story. You're actually checking layer adhesion too. If the temp is too low, the plastic might look perfectly smooth with no strings, but there isn't enough thermal energy to actually fused layers together.
So the part just becomes super brittle.
Exactly. So you actually need to take the cower and physically try to snap it. You might find a block that looks a little stringy, but is structurally indestructible.
So calibration solves like 90% of issues before the real print even starts.
Oh, for sure. It makes your results repeatable.
Okay, so you run these calibrations. You have your flow rate, your pressure advance, your temperature. Where do you actually put this data?
Well, this leads us to OrcaSlicer's 3-tiered profile architecture.
Right, it splits things into 3 profiles: printer, filament, and process.
Think of it like a kitchen setup.
Okay, I like food analogies.
The printer profile is your oven. It holds physical parameters like your build plate size, max speeds, start and end G-code, things that don't change.
Got it.
The filament profile is your ingredients. That is your material properties, temperatures, retract distance, max volumetric speed.
And the process profile.
That is the recipe, the specific print job details.
Yeah.
Your layer height, infill density, wall loops, supports.
So I can swap out the recipe without having to buy a new oven.
Exactly. The practical benefit of this separation is huge. Say you tweak the retract distance for a really damp roll of PTG. You save that in the filament profile. It applies to every single print using that material going forward. You eliminate repetitive errors.
That brings us to the absolute most important habit you can build in OrcaSlicer. We need to pause right here and clearly state this because this is the key tip of this entire deep dive.
Yes, this is crucial.
Never, ever overwrite or edit the default system presets.
The ones with the little lock icon, leave them alone.
Exactly. Always use the Save As button to duplicate the profile and name it really clearly based on your calibrations. For example, name it something like PLA Polymaker 0.4 millimeter calibrated.
Right, because if you mess up the bridging settings or whatever, you always have that clean system fallback.
Okay, let's actually apply this tip to some everyday materials. Let's talk about mastering PLA, PTG, and ABS.
Well, PLA is easy. It usually works right out of the box.
Yeah, 210 degrees on the HO10, 60 on the bed.
And 100% cooling fan, practically the whole time.
But then you switch to PTG, and that exact same cooling will ruin the print.
Oh, absolutely. PTG needs distinct changes. HO10 goes up to 235 or 245 degrees. But crucially, you have to drop the cooling fan to 30 to 50%.
Why is that so critical?
Because too much airflow destroys layer adhesion with PTG. If you cool it too fast, it shrinks rapidly and creates internal shear stress. The part will just shatter.
Wow, okay. And what about retraction for PTG?
You actually want to shorten the retraction distance to avoid stringing and clogs.
All right, what about ABS and ASA?
Totally different beast. You absolutely require an enclosure. The cooling fan should be off entirely.
Because it shrinks so much when it cools.
Right. And you have to remember, ABS requires its own separate pressure advance calibration. Its viscosity is totally different from PLA.
Okay, so the foundation is set. Materials are tuned. Now I want to push the machine. Let's talk about speed limitations.
Yeah, new users always try to push speeds way too high.
They just type in 300 millimeters a second and hope it works.
And it fails.
Yeah.
Because they ignore max volumetric speed, or MVS.
Let's define MVS, because it is the hard limit on printing.
MVS is a measurement of exactly how much plastic the HO10 can physically melt per second.
Right, it doesn't matter how fast your motors are if the plastic is still solid.
Exactly. For a standard 0.4 millimeter nozzle printing PLA, the MVS ceiling is typically around 12 to 15 cubic millimeters per second.
12 to 15, that is a very specific limit.
It is. And the beauty of OrcaSlicer is that if you tell the slicer to go faster than this, like you ask for 300 millimeters a second infill, OrcaSlicer will automatically cap the speed to prevent a failure.
That is so smart. It dynamically throttles the G-code to respect the physics of your heater block.
Yeah, it protects the print from your own ambition.
So what about quality features? Because OrcaSlicer has some really cool mathematical tricks under the hood.
The best one is arc fitting.
Right, using G2 and G3 commands. Explain how that works.
Well, normally an STL is just tiny straight lines. To print a curve, the slicer spits out hundreds of tiny, jagged line segments.
Which can overwhelm the printer's processor.
Exactly, causing stutters and bad surface quality. Arc fitting analyzes the path, realizes it's a curve, and replaces all those tiny lines with smooth mathematical arcs.
It just tells the printer to draw a continuous curve.
Yes, it reduces the file size and drastically improves the quality of curved surfaces.
Okay, let's look at workflow efficiencies. OrcaSlicer allows you to host multiple build plates within a single 0.3 mlf project file.
It is such a good feature.
But, I usually just print one functional part at a time. Why would I want 4 different build plates cluttering up my screen in one project?
Well, for multi-part projects, having them all on separate plates in one single file is a massive advantage.
How so?
It allows the slicer to calculate the total filament usage and the total print time across the entire project at once.
Oh, so you know exactly how much of a spool you need before you even start plate 1.
Exactly. And it ensures consistent settings across a batch of parts. If you change a wall thickness in the master profile, it updates every plate in the project instantly.
That is incredibly efficient. So we've walked through the setup, the calibration suite, the material science, and the workflow limit.
We really tore it down.
Yeah, it becomes obvious why taking the time to master this specific software pays off so heavily.
It really does. And, looking at how integrated slicers are becoming with the hardware, it leaves you with something pretty wild to ponder.
Oh, what's that?
Well, as these systems get smarter, how long will it be before manual calibration towers are just completely obsolete?
What do you mean, like no more printing pressure advance lines?
Right. Imagine a future, maybe pretty soon, where your printer's camera or a micro LiDAR sensor actually reads its own flow rate test in real time.
Wait, really? It just scans it while it prints?
Yeah, it scans the extrusion on the fly and automatically updates your OrcaSlicer filament profile in real time over the network.
That would be unbelievable, a self-calibrating workshop.
Exactly. That is where all this open source architecture is ultimately heading.
That is an amazing thought to leave off on. I'm definitely going to be watching the GitHub repository to see when that drops. For the full numbers, see printera3d.com.